In today's video, we're going to look at another stats test called chi-squared, and this is again something you can use in your NEA projects for A-level geography. It's on the OCR spec, as I have highlighted here, and it's also good for just learning significance testing. So why we would use it and the kind of basic rules, we would use it for comparison. So we're looking at observed data, so that would be primary data we collected, and kind of expected data. What I mean by expected data is what kind of theoretically we might get if the results were completely produced by chance. So I'll explain that a little bit more detail later on. The kind of rules that we need to know, that the data has to be put into firm categories. We can't use percentages, and I'll show you again that later. We need to have 20 observed values in total, and in each frequency, so in each category, and the expected frequency, it needs to be at least 4. Again, I'll point out in our actual data set what this looks like so we can check that our data is valid to be used. So here's a hypothetical investigation I'm doing where I'm going to hopefully use a chi-squared test. So I'm doing a study in a school on whether students identify more national flags as they get older. I get some year 9s, year 10s, 11s and 12s together. I get the same number in each year group and I show them 50 national flags. What I'm actually recording, my observed data, is I record how many of those students in each year group can identify 20 flags. And then I'm going to test to see is there any kind of significance between your age and how many flags you can mention. So if I get set up a null hypothesis for my test, it would say that the distribution of students in a school who can identify 20 flags is random and occurs by chance. It's essentially saying that there's no kind of relationship with the age. Pretty much anyone could identify 20 flags. There isn't kind of a significant pattern. So I'm going to test this. So the first thing I need to do is I need to collect the data, and I've collected it here. This is what we call my observed data. So year 9, 5 people could do 20 flags or more, 9 in year 10, 10 in year 11, and 20 in year 12. And I've added them all up and there's 44. So first of all these frequencies are above 4. And also the total is above 20. So those are the criteria I need to have to be able to do a chi-squared test, so I can actually do a chi-squared test to this data. So I've got my observed data, and then what I'm gonna do with this, I'm gonna put this eventually into this formula, which looks a bit like this. We're gonna work out x squared, and I'm gonna explain what expected value means in a second. But just a couple of things, that kind of funny symbol means the sum of, so the kind of total of all this equation. But also the expected value is that kind of idea of what we might expect to see if the distribution is random. Again, I'll explain that in an example in a second. So in terms of hypothesis, if my x squared value that I get at the end, if it's larger than the critical value we compare it with, then we're going to reject the null hypothesis. And if the x squared is smaller than the critical value, we accept the null hypothesis. This will be explained through the example I'm going to use, but you might want to come back to this page just to clarify those rules right at the end when concluding whether the test is significant or not. So I've collected this as data and I've changed that type just to show that it's the observed frequency, but that's the data I've collected. So I need to now work out the expected value. And I do this by I divide that total at the end by the number of categories. So I've got 4 categories because I've got 4 different year groups, and I've got 44. So I divide 44 by 4 and I get 11. And so what I would do is I put it into my table like this. The next thing I need to do is for each category I need to take the observed frequency from the expected. So I need to take it away. Simple subtraction, so it would be 5 minus 11 in the first category, and I would get minus 6, minus 2, minus 1, minus 9. Again, simple taking away, not too complicated. The next thing I then need to do is then I square that difference. So I can get part of the equation, which is this O minus E squared. Again, minus 6 times minus 6 will give me 36, and I do the same for the rest of those categories and I add them into my table. Last thing I need to do is I finally divide that figure that I've just got by the expected frequency. So I've already got the expected frequency in my table up there, and that's 11, and then I'm dividing it by my last figure that I've just got, and again I get all these different figures that I just put into the table below. So if you just do it step by step, it's quite simple to do. Eventually I need to work out what the x squared is, and how I do that is I add all those values I've got in that bottom column, and I get x value. So if I add all these up, then I actually get a score of 11.08. So that is what I'm going to test against the critical value. What I need for this is one of these critical value tables, and you can find them anywhere. This one is the one I'm going to use. And what's to get the degree, I need to work out the degrees of freedom that I compare it to. So all that means is I look at the number of categories that I've got, and in this case that was 4 because I did year 9, 10, 11 and 12, and then I minus by 1. That means that when I am doing my degrees of freedom to the critical value, I'm doing it to 3 degrees of freedom. So I look on my table, and the 3 degrees of freedom at the 0.05 significance, so that would be, is this 95% significant, is 7.82. That's an important figure because I need to compare that to my x squared figure. So the x squared value that I've already worked out is 11.08, and that is actually larger than this figure, 7.82. If we go back in the video, we'll see that if the 11.08, the figure that I obtain, the x squared, is larger than whatever I get in this column, we therefore reject the null hypothesis. So that essentially it kind of finishes my investigation, but then what does that actually mean? So in terms of the investigation I did, if we're rejecting the null hypothesis, we can state that the idea that the distribution of students in the school who can identify 20 fags does not occur purely by chance. If we were accepting the hypothesis, it would say that it is purely by chance. Therefore, I can make an argument to say there's an association between the year that someone is in at school and the number of flags that I identify. Therefore, I can use that to analyse the data that I've collected, and I can potentially explain why that happens. So this is a really useful test to use for an NEA or a project, and what I'd recommend is go back through the video and do it step by step, and then apply it to your own data.